going to talk about vectors. And this is the most important thing. Vectors have magnitude and direction. They don't have a starting and an ending place. So all three of these vectors, PQ, RS, and TU, they're all equal because they all are in the same direction and they have the same magnitude. How can I tell? This is not how you would always tell, but if I was looking here, I could count 1, 2, 3, to the right 4 and up 3, 2, 3, 4, to the right 4 and up 3, to the right 4 and up 3. Because I know that they're all going to the right 4 and up 3, all those angles are the same and all those lengths are the same. When we add vectors, we can add them geometrically. And when we add them geometrically, for example, if I want to add V plus W, here's my initial point, here's my end point. And sometimes we call this the head and the tail. A lot of times you'll hear this is the tail and this is the head of the vector. When I learned it, that's what I learned. But also the initial and the terminal point. When you want to add vectors, the first thing you do is you put the first one down and then you put the tail or the initial point of the second vector to the terminal point of the first vector. And if I want to add them together, I go from my initial point to my final terminal point, which is here. So this vector right here in green is actually V plus W. I promise we'll do it in a little bit without it already being there, just so you can see, but that's basically how it works. What do we know about vector addition? It's commutative. Not every type of function is commutative, but vector addition is commutative because it doesn't matter. So commutativity means it doesn't matter what order I add them in. So V plus W equals W plus V. And here's a picture of it. I can start with V and then add W, or I can start with W and then add V. And you can see that both of them have the same V plus W and W plus V. We do know vectors are commutative. They're also associative. So associative property means it doesn't matter which two variables I do first. So for example, because these are in parentheses, I would normally add those first and then add U afterwards. But that's the same as adding U plus V first and then adding W next. So that's the associative property, and vectors also have the associative property. V plus 0 is 0 plus V is just V. So if we add no vector to the original vector, we get the original vector. But here what's really important is that if this is V, and here is my initial point, and here is my terminal point, then if I want negative V, it's the same magnitude in the exact opposite direction, like 180 degrees in the opposite direction. So this is now my initial, and this would be my terminal. And it is true that if I add V plus negative V, I do get 0, because basically I'm going somewhere, I go to the end there, and then my next vector, I start here, and it goes exactly the same. So I go back to my starting place, which means I didn't move at all. When we talk about a scalar, this is basically talking about a constant. When you scale something, you're proportionately making it bigger or smaller. If alpha is a scalar and V is a vector, the scalar product is alpha times V. If here I start with my V, which is going 3 to the right and up 2, then, well, let's do this negative V. It's going notice how it's going the opposite direction. So it's going down 2 and to the left 3. And then 2v should be double. So here we're going across to the right 3 and up 2. So we should be going to the right 6 and up 4. Let's just see what happens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. All we do, we're doubling it. And we're doubling the x and we're doubling the y values. Let's read through number 1, 2, and 3. So 1, if alpha is greater than 0, the product alpha times v is the vector whose magnitude is alpha times the magnitude of v, but the direction is going to be the same. Notice all of these have the same direction. All we're doing is stretching them out. If alpha is less than 0, the product alpha times v is the vector whose magnitude is still the absolute value of alpha times the magnitude of v, and the direction is in the opposite direction, just like I said. And if alpha equals 0, or if the vector v equals 0, then alpha times v equals 0. So notice here that we have, whenever they're talking about a vector, notice how it's bolded. That's one way that you can designate a vector, but that's really hard. It's a very hard way to designate a vector when you're writing. We write vectors in multiple ways, and we'll see a few of them. A vector would look like that. That means that I have a vector. Or what other notations? But this is a real popular notation for a vector. It just has that little, almost like half arrow up on top. Properties of vectors. All the bold letters are vectors, and the not bold are not vectors. Okay, as you can see here, all these are vectors, and these are real numbers. We could call them scalar, we can call them constants, but they're not vectors. We are not multiplying vectors times vectors in this class. I'll run through it really quickly. We know all of this. 1 times u is equal to u. If you multiply by 0, you get 0. This, we already talked about, this is commutative. Now notice here, we're saying that when we subtract 2 vectors, it's the same as adding a negative vector. And that's going to be important when we talk about doing something geometrically, not necessarily if we're doing it algebraically. This we already talked about, that's the associative property. And notice here, all that you can do whatever you want as long as you only use constants. You can't multiply vectors that way. U plus 0 equals u, we talked about. And if I add the positive and negative vector, we get 0. As long as you have a constant, it can distribute. Either way, this is distributing as well.